The last thing that we want to talk about with conservation of energy is where potential energy actually comes from, and it's because of these things called conservative forces. So a conservative force, what is that? A conservative force is one where the work done by the force depends only on the starting and ending points of the motion. In other words, the path taken doesn't matter. So if I start here and I end here, then it doesn't matter if I go all wavy like this, or kind of in spirals like that, or in a straight line. All three of these motions, 1, 2, and 3, will have the same change in same amount of work done. So in other words, you can kind of think about like in the one case, any sort of upward or downward motion cancels out because ultimately end up in the same position. Same thing with any left and right motion beyond just getting over to this point. That extra stuff cancels out. So examples of this: gravitational energy or gravitational force, spring force or elastic force, and what's the last one? Electrical force. So the electrostatic force. In all of these cases, you can move a particle or stretch or fly around all over however you want. All that matters is your starting and ending points and how those compare. Non-conservative forces, in this case, the work done depends on the path taken. So back to our previous example of comparing 2 points, you'll get a different amount, it was roughly like this, you'll get a different amount of work done for each of these paths because they look different, they're shaped different. For example, path 3 is a lot longer than path 1. So examples of this, the main example we have is friction. Because friction is always going to oppose motion, it's not going to be able to let you reclaim energy when you go back the way you came. Whereas with gravitational, if you push something up, but then you lower it back down, that energy comes back out. With friction, if you push something up, you have to push it back and then it comes back down. In both ways, energy is being taken out. Energy is never going into the system. So what does this mean for potential energies? All potential energies are the result of a conservative force. And this means that work can be stored and then later released, hence it being a potential energy. So what we mean by that is you can, for example, if you have a box, you can take that box and you can move it up on top of the counter. You can do work against the gravitational force and you can put it on top of the counter. And then later you can push that box off the counter and that energy that you had stored, lifting it up, is released as it falls back to the earth. The conservative nature of gravitational force means that the work that you put in lifting it up is then later released when you lower it down. And this is actually one way that we are looking at storing energy in the future is, for example, putting giant blocks or giant masses on cables. When we have energy, storing it by lifting it up in the air, then we want to release that, we can let it slowly lower back down and have it turn basically a generator to release that energy later. Or we do this for sure, definitely now, where we will have, say, a pool of water down here and another pool of water up top. and then a dam in between, we'll pump water up with like solar power during the day. We'll use that to run a pump to move water into the upper reservoir. And then at night, when we want to get energy back out, we'll release it through the dam and have it run through a hydroelectric generator. So in other words, this is storing energy as gravitational potential energy. We pump it up during the day when we have sunlight, and then if we need energy at night, we can let it run through back down and collect that energy back. And so those are our two examples if you want to write those down. Non-conservative forces and where those come into play with energy, these typically cause a system to lose energy. So energy is moved into a system like thermal, internal thermal energy, where it can't easily be released. So right, if I rub my hands together a lot and generate a lot of friction, I can't like release that energy to have my hands start moving again. Or if I drag a box, if I shove a box and it gets slowed down by friction, there's no way for that friction to return back to the kinetic energy. Whereas if I throw a ball up in the air, there is a way for that to be turned back into kinetic energy. We just have to let it fall back down to the ground. So for example, like I said, if we have a box and you shove it so it has some KE and it slides and it loses that, or that energy becomes thermal energy because of friction, it's not like you can get it moving the other way and have it release that and speed back up. You know, instead, if you shove it the other direction, you're just gonna have it lose more energy to thermal energy. So the main example here that you're gonna see is, in fact, that friction. And this is why we say that energy is lost as heat. You can also see it with some other things, but friction is the main one.